Welcome, my digital pathology trailblazers. I'm gonna switch off the music because last time I forgot I had it on. When you join, let me know if you are. Well, let me know if you are here. Let me know where you're tuning in from. I actually don't need the headphones if I don't have music on. I see you joining. Let me send you a hi in the chat and just let me know where you are tuning in from, what time it is. And I have this problem always that I want this live stream to be high resolution, and it is not. Well, now it's too late to fix this problem. So, couple of updates as you are joining and as you are saying hi and letting me know where you're tuning in from. So we are today gonna be doing the third part. We're on the third article. Let me see if we have my pen is working. I think last time it was not working. Let me know if you're hearing me well and if you are seeing me out well. If I drop off this live stream, which happened in the past, just wait for me to get back. Should be fine today. But we are today in this place, non-generative AI, ML in medicine. ML is machine learning. And we are not yet halfway through, but getting there. The next one is going to be tough. It's going to be statistics. I need to really prepare for that one. This, like the first three one, I have enough knowledge to basically teach it without too much preparation. This statistics, this is going to take some preparation. Oh, welcome, Trang. This is so cool to have you. Friday 5 a.m. club. Yeah, there was a book, the 5 a.m. club. I never read it, but I think I belong to the club. So the updates for today, other than we're doing the third paper, are uh, that the authors of the papers, well, not all of them, but the main initiators or of this whole session, serious, are these guys. Let me show you. It's gonna be Liron, it's gonna be Human, and it's gonna be Matthew Hanna. Here. They work together at this University of Pittsburgh Medical School, and they are establishing a AI Center of Excellence for Medicine. They were the main driving forces behind this series, and I managed to schedule a date to have them on the podcast. So be excited with me. I'm super excited to have them all on the podcast and talk about what they're like about the series, what was the goal of this, how did it happen that they did it, how long did it take, and all the stuff behind the scenes of writing a paper, which if you have ever, not even if you haven't written a paper, if you have read one, like it's a lot of work. It's tough. Anyway, so they did 7 of them. They are working on the center of excellence. They're being the center of excellence, and they're going to join me on the podcast. So I am super, super excited. And we have Atlanta on the line. Welcome. So cool to have you here, Scott. If you're just joining and I see that you guys are joining, let me know in the chat where you're tuning in from and just say hi. So that was the first update. They are going to be on the podcast and you will be seeing them on video. Then I'm going to be at US Cap. I'm going to be working with, sorry, wrong window, of course. I'm going to be supporting a sponsor, Muse Microscopy, and then I'm going to be creating content with some other sponsors. So most of the time, I'm going to be at this Muse Microscopy booth, which I'm going to tell you which is the number later, once I find it. Then you can meet me there. And probably we will have also a setup to join me on my podcast and basically talk about your digital pathology journey. Doesn't matter if you're a beginner or if you're advanced, if you already implemented something, published, not published, just exploring. I want to hear you there. and I want you to be a guest on my podcast. We're going to be doing mini episodes with you, with the digital pathology trailblazers. So let me just check this, the booth. Because then, if you're going there, and you probably already know that you're going there because the registration is probably like closed. 528, the booth 528, 528. Let me just write it here. US Cap booth 528. It's gonna be Alex and Muse. So join me. Just come and say hi. Whatever you're doing there, if you're just for one day, come to booth 528. And we have international crowd joining, which is fantastic. Hi to Cambodia. Wow, I don't think we have had anybody from Cambodia say hi yet. That's exotic to me. Okay, so that's the second update. And third update is we're gonna I think one time I asked if we wanted an annotation workshop, and the answer was yes, we want an annotation workshop. And I kind of had a shout out in this live stream. Oh, if there is a company who would like to facilitate that and sponsor this live stream, we can do that. So there was a company that reached to me, and we are going to have a call next week to figure out how to do this live stream. They have images, they have the software to annotate, so you guys can just join me and annotate live. And speaking of annotations, that is going to be part of the topic of what we're going to be talking about today, because today we have non-generative AI in medicine. And non-generative, and I'm going to make it big. Let's do this here. And there are guests who are gonna be present at US Cup. So join me, booth 528. Let's see each other. I'm gonna be running around crazy person, but I will be at that booth for a lot of time. So you just say hi, you say I'm a digital pathology trailblazers, and the conversation starts, even if we have not met in person ever, because it doesn't matter. I met a lot of my digital pathology trailblazers at conferences, and it feels like we knew each other for a long time. So yeah, the live stream with annotations is going to happen. I will let you know when. And now let's talk about non-generative AI. Let me not destroy my setup. And also let me like make better lines. What is this line? Like my 6-year-old does better lines than me. Let me remove it. Okay. So if you're just joining, let me know. Oh my goodness, we have many people today. Say hi in the chat and let's do it. Maybe we're not going to sit here for an hour today because they have cool images. Okay, so non-generative AI in medicine, advancements in applications in supervised and unsupervised machine learning. So last time we talked about generative, and now we're talking about non-generative. Let me take you to the first image, and we are here. This is our third session. I skipped the session last week. I'm sorry. I don't know what I had to do. Something crazy for other stuff, and I had to skip. Apologies. So when we look at this image, let me just make it even bigger. Yeah. One more time. We can do it, guys. We can do it. I want to make it bigger and move it around. I think, yes, I'm tech savvy enough to do it. Okay, so starting with this girl, focus. Hierarchical structure of AI technologies. And today we're talking about non-generative AI. AI is the whole thing. Like everything that computers do can be described as AI. And so at the very beginning, we have machine learning, and then part of machine learning is deep learning. Then within deep learning, we have the foundation models. Large language models and vision models are within foundation models. And it can be both generative and non-generative. Last time we talked about generative, now it's non-generative, meaning it doesn't make anything new. It predicts from data. And what can we use this non-generative application for? And I have the tendency that I think I have overcome, but maybe I have not overcome it yet, to be super excited about every new technology. And it's like, I don't know, let's call it new tech toy syndrome. Where I see a new method and I'm like, oh, now I can forget about all this other stuff and I can just use this new method for everything. Never happens. And I keep being so excited. Right. So doesn't matter. So what do I want to say with that? When the generative AI came on the scene, I was like, oh, we can like throw everything away from the non-generative. And of course, as I learn about the technology and about the limitations of the technology, I'm like, if we would pull this one approach and use it in combination, or this other approach, or maybe like you don't really need to deploy generative if your task at hand is so simple. So every time a new thing shows up, this happens to me. I kind of already control myself, but not always. I always get this excitement. So, what can we use these non-generative AI foundation model tasks in pathology and medicine? We can use them for quality control, ensuring data quality, and detecting artifacts in hostile images. We can use it for classification. So here we have a couple of words that have um, kind of double context. Classification, for example, it's a normal word where you classify something, but it's also a concept in computer vision, where you classify things, but by a computer, right? So a very common classification task, and these are called tasks. The things that the computer do. Classification task is identifying disease and detecting abnormalities based on the whole pathology or radiology image, cancer versus normal. So these are the algorithms that will help pathologists do something on the images. Then we have object detection. Like the name says, it detects objects. So it spots specific cells or features in pathology or medical images. And in computer vision tools, this object detection, there is something like a bounding box. So let's do, if I want to do object detection of these, what are pentagons? Pentagons? No, pentangles. I don't know. Send me in the chat. Like, I know a hexagon and I know a rectangle. What's a 5? Let me know in the chat. Anyway, if I wanted to do object detection of this, if I was a computer, I would place a bounding box around it that would have, and each of them would have a bounding box, right? So this is a real thing, a bounding box. You basically place a box around the stuff that you're detecting. And also, this can be used for different cell detections. So, Chi67 quantification, the blood smear quantification, cell quantification. Whenever you need an object, just to identify an object, you would use this. If you need to outline a region, you would use segmentation. And this is another computer vision word that means that you're going to be outlining a region. Maybe I do this one. Outlining a region of interest in medical images. For example, tumor in pathology images, where you have in the image analysis, you would do tumor stroma separation. If you only want to, for example, identify immune cells within the tumor or within the pentagon. Yeah, pentagon was correct. Okay. Thank you so much, Pedro, for pentagon. I was like, pentagon, was that not the military place? Anyway, but yeah, so segmentation for regions, for example, segmenting cancer, segmenting, I don't know, specific regions of an organ, segmenting vessels, something that you want to extract out of an image, but it's not an object, it's a region. So objects are the cells and regions are regions, right? And then we have something called anomaly detection, which when I heard about it, I was also super enthusiastic, because I'm a toxicologic pathologist, and the job of a toxicologic pathologist is to most of the stuff is normal, but not only in toxicologic pathology, also in diagnostic. Most of the stuff is normal, and then you want to train a model on normal so that it can tell you when it's abnormal. And I was like, this is a fantastic concept. Let's just do this. And I will keep just looking at the abnormal as long as I don't have to like visually screen. Well, it didn't perform that well because the very subtle changes that toxicologic pathologists evaluate are very subtle. So they don't look such like as such an anomaly. You like hunt for the change. Anyway, so these are the things you can do with the classical non-generative AI, and they are still um, like legitimate things to do where you can use these tools. And we can divide the AIs in supervised and unsupervised learning, and we're going to start with supervised learning. So supervised learning, let me just check if I have some text that I want to mention as well. Yeah, but we focus on the images because image is worth 1,000 words. Supervised learning. And if you have any questions, let me know just what questions you have about what I'm speaking right now so that I can address it immediately, or anything else related to digital pathology. Just let me. Supervised learning is with labels. What are labels? These are like names of things. This is a phone. So if I had an image and a label, it would be an image of this phone, and the label would be phone. And in medicine, label is going to be the diagnosis, for example, for an image, for a pathology image. It can be the diagnosis, it can be an annotation, it can be at the whole report now with generative AI. So now the generative and non-generative is going to be intertwined, but the whole report can be a label for this image where you have descriptions, what's on this image. So basically pairs of something and then something that's telling you what that is. And in supervised learning, and the types that we have, there is classification and there is regression. And you can see on these images are brilliant. I love them. So classification, you have a bunch of dots, and then you want to divide them in some group, classify them into blues and oranges. Yeah. So that is going to be classification. You classify them into one of the classes. Classes are the categories. And regression is, oh, they are all like together. So you do a line around which these things are. So this is linear regression. And there are also different algorithms. So these are the types of supervised learning. Sorry. Types of supervised learning. And there are also different algorithms, which every time, so I've been doing this, or I've been in that space since 2016. Oh my goodness, that's like 9 years already. Crazy. Next year I can say I have a decade of experience in blah 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 in this space. Anyway, but what I'm getting at is I remember when the random forest decision tree came out and we started using it in the tissue, the image analysis company I was working for, tumor stroma separation, and I saw a few images and they were so good, and I'm like, let's scrap again, right? Let's scrap all the other stuff that we did because this is so much better. And then on other images it didn't perform. So then again, when deep learning came on the scene, I was like, oh no, this random forest is like so random, let's not use it. Let's do deep learning. And then I learned about the limitations of deep learning. So with before I tell you what it is all about, we say hi to Argentina. Hello. But I'm just, kind of making fun of myself to emphasize that there is a right tool for everything. There is no one tool for everything, right? Mm, and, I'm just super excited about stuff. So, and I think one thing is going to solve the problems of the world. So, decision tree, where you basically make little decisions, support vector machine, and we have a little text about it. I'm going to go into that text with these because there is a little bit more explanation needed. We have linear and logistic regression, and linear, you can see that there's a line, and logistics, we have like two groups of points, and there is this S-curved. I'm going to remove them, making this images any better. Then we have K nearest neighbor, and here is our neighbor in question. And we decided that it's actually closer to blue group, so we're going to instead of yellow. And the neural networks. So they are better than the other approaches for image analysis. They're not perfect, right? But they're definitely better. And here we have a real life example of I think, and segmentation, detection and segmentation and classification as well of digitized PAP test slide, right? So here we have what cells are here: normal cells, abnormal, metaplastic, and then we have also squamous cells and glandular cells. So squamous are from the surface or from the surface of the cervix in this case, but also we have glandular cells, endocervical and endometrial, and these are our classes, the categories, the classes. And there are different features of these things. They can be geometric features, nuclear to cytoplasmic ratio. We can have HPV status, and this deep neural network does feature detection, and deep neural network has this input layer. Then stuff is happening in between, and this is what is often referred to as the black box ability of AI. What's in the black box? You have input and then you have output, but what happened here? And things happen like convolutions and basically different computational calculations happen in there. And it's called neural network because these circles are called so-called neurons, and it resembles the connections in the brain. And then what we get from this output layer, we're going to have some quantification, we're going to have classification, we're going to detect the cells, and we're going to segment them. So that's what can happen with deep learning. And our deep learning neural networks were here, one of the common supervised algorithms. And here you give a lot of these examples. So that's going to be often a human labeling it. And in case of pathology, it's going to be a pathologist or a histotechnologist or whoever has the domain knowledge to consistently recognize and classify these cells. So let's talk a little bit about the theory. Decision trees. I'm going to move it a little bit. If you have any questions, let me know. Decision trees. This was a popular non-parametric choice for supervised machine learning in medicine and pathology. And building such tree-based machine learning models can predict patient outcomes, diagnose disease, and sometimes help identify new biomarkers. Do you notice there's no mention of can analyze images well? We used it for image analysis, but you take the newest thing and you check if it works. But yeah, these are still popular and useful. Then we have the support vector machines, and I'm going to be going back to the image so that you have. So decision tree was here. Then we have the support vector, right? And you see you have two groups of dots and some line in between, right? So let's go to theory of support vector machines. They excel at handling high dimension data and can be used for classification tasks. So the main goal is to find optimal boundaries, so-called hyperplane. So that was the line in the middle, hyperplane, that separates labeled data points of different classes. And in two-dimensional space, the hyperplane is a line, right? It doesn't have to it doesn't have to be flat. It can be in the space, but then you have hyperplane that becomes a line. And data points closest to this line are referred to as support vectors. And then if a trained support vector machine model is presented with a completely new data point, it can be used to predict on which side of the hyperplane it will end up. So it can classify disease. And from continuous data, a regression approach can be used with support vector machine. So it's a combination. It's called support vector regression. And let me show you. Here was regression. This was regression, like checking, like kind of like retrospectively saying on which line these points are, around which line they are clustering. So you can combine this support vector, and you can probably combine everything, but that's the example we have here. And so let's talk a little bit about regression. Linear regression is denoted by a straight line, as we have seen, where logistic regression reveals, logistic is the other one. I'm going to be scrolling a little bit. So this one is the logistic, and you can see barely because it's small. Maybe I can make it bigger. We will lose resolution, but it doesn't matter. This one is an S-shaped curve, right? Okay. And this linear logistic, so linear is straight, logistic is S-shaped, and in contrast to linear regression tasks, logistic regression is often employed for binary or ordinal classification tasks, such as diagnosing the presence or absence of disease. And you had the points clustered above and points clustered below. Whereas the linear is going to be for continuous outcomes, such as blood pressure or glucose levels, right? Then we have K nearest neighbor, where the yellow dot became whatever it became, blue, I think. Yeah, we decided it's blue because it's closer to the blues. And this can be employed for classification and regression tasks. And K nearest neighbor model does not require a training phase. And they are also sometimes called lazy algorithms because computation is delayed until the prediction phase. That means that the computation is expensive because it's so delayed. And what can we use it for? For diagnose, classify. So here, see, they often say this diagnose, classify together. The classify is in brackets because diagnose is medical term, classify is going to be computer vision term. And let me show you something. I have it in my book, a little diagram. I call it computer vision to pathology vision translation with giraffe images. If you have the book, it's on page 77. Maybe I can just look. Let's see if you guys can see it. I should have a PDF ready, but basically, you will not see it well. The giraffes, right? And this giraffe has just a box around all the giraffes. And this is a classification, it's classifying these are giraffes. Here, this one has a bounding box around each of the giraffes. There are 3. So this is object detection. Then you have all the giraffes together. We actually, do you hear me? Let me know if you don't. We delineated the giraffes. So that's going to be the segmentation. We segmented them. And here, a certain type of segmentation, semantic segmentation. And here, we actually segmented out every single giraffe, which is called instance segmentation. So these are the computer vision terms that you use to solve pathology problems. And pathology problems will be structures of interest, which are the dots and cells, and tasks of interest. And structures, we will have regions, and objects, we will have cells. And next time, if I want to show it, I'm going to prepare it in the digital version. So, but if you have the digital, you can get the digital version on digitalpathologyplace.com. There's like a big button, and you can just download this book for free right now if you want to. I should have a QR code for that next time. Okay, going back to our task at hand. If you have the book, let me know in the chat. Just write book in the chat. Or if you want it, write want the book, and I'm going to send you the link because I didn't prepare the QR code. Apologies. And then we have the neural networks, the almost magic. And neural networks, it's okay. We had a good image for this one, so we're going to skip the theoretical explanation. And then application and performance of supervised learning models. We're going to talk about performance next week, but let's talk about the application. What can we use these models for? And like, how will you use it before we dive into it? Like, how will you use it as a pathologist? Like, now you're going to be going to your IT people or to your computational pathology team and saying, oh, let's use regression for this and let's use this one for that. I wouldn't do it, but because I'm not a computer scientist, but I can now constructively discuss different approaches because I have the knowledge of the pathology tasks and what I want, like what do I want to get, what information do I want to get, and I know the names of the tools for and what those tools are good for, and I can now explain to my computational pathology team, hey, this is a task at hand, these are the computational computer vision terms of the things that I want to achieve. Which approach do you think is best? Maybe that one, maybe some other one, maybe don't use random forest for tumor stroma separation. At least when I was doing this, it didn't work that well. But anyway, the example is like you need to have enough background knowledge to work in a multidisciplinary team, and digital pathology team is a multidisciplinary team. And we are part of this team, so we need to know how to talk to others. And what can we use the stuff for? So, for example, regression models generating continuous numerical values output can be trained on a data set of patient demographics, medical history, laboratory test results, along with, for example, cost of each test, and then labs can predict cost savings, right, from this kind of stuff. In pathology, the supervised machine learning is used for classification models and discrete class outputs that diagnose disease from labeled data. And the convolutional neural networks have been a cornerstone of modern AI within image classification studies, right? So both radiology, pathology, you want to screen, you want to say benign, malignant, cancer, no cancer. This is going to be classification. The method is the leverage is going to be convolutional neural networks, and because they can convert pixel data from images into progressively higher order visual features over the course of sequential convolution and pooling steps. And these steps are what is happening in the black box. And if you are just joining, let me know in the chat. And then we have unsupervised learning. So the supervised was with labels, unsupervised is without labels. And what do we have here? We have clustering, we have dimensionality reduction, and anomaly detection. Clustering, that we cluster some data points into groups, right? And in an unsupervised fashion, these groups are being selected. And I mean, I would do this group as well here. Yeah, probably. I will do the same. I will do the same as the algorithm does. And now we have three groups, and we can check, okay, what do they have in common? Do they have some gene expression in common? Do they have some test results based on, the data that you have? The algorithm is going to cluster them based on this information. Sometimes we have a lot of information, and not all of this information is relevant. So then, dimensionality reduction would be something that could be used, and anomaly detection, that I still believe it's going to get better, and then we can detect all these red dots, even if they're very subtly abnormal. But that's an option as well. So the model only knows normal, and flags everything that is abnormal. And the algorithms used here is k-means clustering, so making these clusters, principal component analysis. So here you figure out which groups these belong to, so-called principal component analysis. Tisna, one time I remembered the um, if you know, let me know in the chat, or you can Google it and put it in the chat. But basically, this is actually a way of visualizing stuff, like a 3D relationships between data into a 2D plane. Tisna plot. This is a Tisna plot. So clustering is going to group similar data points into clusters. Easy name, right? And based on their feature similarities, and this is fun. This is, well, fun. It's interesting. Randomly initializing k-centroids, or cluster centers. And the keyword here is randomly. So it just like randomly initiates a center of a cluster and makes a cluster, which brings me to mm, something about the unsupervised methods, is that it's not always easy to interpret why this was clustered together. You have to investigate, does it make sense, or is it being clustered based on irrelevant information, or relevant, and which kind of information that takes us again to the explainability aspect of AI. In the supervised learning, there is a label, right? So you can compare it to the label, whereas in unsupervised, it's just figuring out which data belongs together, and you can then, as a researcher, you need to check, does it make sense. So, in pathology, has been applied to identify subtypes of disease, such as different cancer subtypes, patient subgroups with distinct clinical features of gene expression profiles. And the cool thing is that it can enable researchers and clinicians to uncover hidden patterns in different data sets. So if the data is if there is a lot of data, if this is a multidimensional, uncovering these patterns with your eyes or with your own mind is difficult. So you has leverage. And then the dimensionality reduction, also name says it all, reduce the number of dimensions, features in relation to original numbers. So basically eliminate everything that does not give you additional information to classify this data into categories. So, while preserving the most important information. And so, for example, this is used to simplify AI models, compress data, reduce noise, improve performance, prevent overfitting, and reduce computational costs. And there is a trend or tendency that I'm seeing is, and this is often mentioned as a drawback. Oh, and we have more international guests now from Cameroon. Fantastic, Cameroon. Welcome. So the trend that I'm seeing, I think it's just a general tech trend that's happening, and then it's entering pathology AI world as well. That you have this, it's actually everywhere. Like life is a funnel, right? You have a highly computationally how do you say, like, that consume a lot of computational resources, and then an algorithm that consumes a lot of resources, and then you figure out how to streamline it, how to get the, like, with this dimensionality reduction, you have a bunch of data that classifies it into something. Oh, can it use less data to get the same result? Can it use less computation to get the same result? Can it like not use the whole image at one time, but like stream the image, and different ways to make these new computational discoveries lean, which is super important in medicine, not only, but in general, to put it in devices that have less computational power than computers, than servers, and things like that. So, very important for medical devices to lean and trim off the unnecessary computational resources that are being used. Then we had our anomaly detection, outlier detection, which is unsupervised algorithms used to identify outliers. And this can be applied to pinpoint unusual patient records with a particular health issue, error in data entry, detect rare genetic mutations, identify errors, or flag abnormal lab results. So you immediately, whoa, excuse me, I dropped my pen. Immediately have something flagged, right, to for further workup. Super useful. And let's look at here. We have the fully supervised learning, weekly supervised learning, and self-supervised learning. So let's start with fully supervised. Who has done annotations in this group? Let me know in the chat. Have you annotated pathology images or any kind of like images, and not just hours at a time? Then you know why I'm making faces. And this is also the bottleneck of this approach. It's a blessing and a curse at the same time, because blessing, you have an expert, or maybe you have some other orthogonal label, which is fantastic because you then don't have to have a human label stuff, but then you have a different cost associated, pros and cons of everything. But basically, this is going to be a slide plus an annotation or region of interest labels. And then you sample regions of interest using annotation, and then you have a predictor, and then you update this predictor using more more annotations. So you give the model some annotations, then it trains a little bit, you see where it is making mistakes, you give more annotations, and then you can basically train a very good image analysis model. But if you want to use less human resources and not annotate so much, you can just use slide and the slide label. So what's going to be the slide label? The slide label is going to be the diagnosis of the cancer that's on the slide. Or like a case label, where you have a bunch of slides together. Not all of them have cancer, but in general, the case has cancer, right? And then here we're going to be we're going to use attention mechanism, and then the model is going to predict the slide, and it's going to go back to these predictions and update them as it trains. So this is the weekly supervised. And then we have self-supervised things. Let me remove my too colorful on this image. A little bit too colorful. And if you have any questions, you let me know in the chat. Just want to remove this. Well, I don't know if it helped, but what I want to say is that self-supervised learning basically eliminates the person labeling. And Thomas, I know you feel my pain about annotations. You're smiling. Yeah, I mean, it's a blessing and a curse. It's a tedious task, and you do need high quality data, so you do need to like put some effort into it if you want to have a good model at the end of the process, right? And the more data you feed the model, the better. So the more you annotate, the better. The more you annotate, the more tired you are, and you know that's, I guess that's life. That's okay. Anyway, so self-supervised learning. We have the slide tiles. We have perturbation, perturbed slide, and tile. So what did we have? Okay, here it had the yellow, and here it has green. Then we have an encoder model, training loss, no label, and downstream use may require further training. And here it's basically matching stuff and also reconstructing stuff. So it didn't match circle and this other thing, but it matched the two stars, right? And then it's reconstructing. And the update encoder model using loss function that do not need class labels. And this borders on magic for me, but it's not magic. It's just the new um, computational ways of doing things, which I love because in the last, I think, 2 years, I stopped thinking about this 1 second. Sorry, I didn't take water, and I have to mute myself to cough. So in the last 2 years, I would say, maybe even more, but in the time when, okay, so there was deep learning first that I learned about. It was before, but I learned about it like 2017, 18, and that bordered on magic for image analysis. But then the large language models came out in 2021, 2022, and I'm like, okay, if there is something that's not working right now in terms of AI, I don't have to get frustrated. I just need to wait, because those people are like constantly iterating and figuring out how to make these things better. And sure enough, there was something that I think it was the molecular prediction from images, from because you can have molecular information as a label and then have a predictor of molecular stuff in an image. And I started seeing these publications. I'm like, okay, you just wait, keep following this field, and they will come up with something cool, a cool method. And then us as the scientists, pathologists, healthcare professionals, and whatever expertise we have, being aware of those methods, we know how to leverage it for our fields. We're not done yet. Let's finish up. So, and then I'm going to go to the comments. I have a few from Thomas. So, digital pathology and non-generative AI machine learning leverages whole slide images, right? We know it leverages whole slide images. As we said, can be labeled and linking the slide with diagnosis or metadata. And metadata is basically data about data. So it can be patient demographics, clinical findings, tumor grade, stage, immunohistochemical results, response to therapy, and you name it. You can figure out what other data can be there. And the term of annotation refers to process of marking or labeling specific structures, cells, mitotic figures. Oh my goodness, can you imagine sitting for 5 hours and marking mitotic figures? And people did that, and they did that well, and then came with a good algorithm for mitotic figures. And these annotations can be performed using digital tools. And when we have the annotation workshop, and if you have some data that is like that can be shown, and you would like me to do an annotation session on your data, and we can do it, in QPath, or if you're a vendor, we can do it in your software as well. And then you can reach out to me, and we can organize that and do some. That's going to be a fun annotation session. I know I'm like complaining about those annotation all the time, but on the other hand, you can put music on and you can hang out while annotating, and that's what we can do. So yeah, digital tools, overlaying bounding boxes depending on what the task is, right? Different colors on H&E images can be done in open source, which QPath is the main open source, or commercial tools. V7 is one. And then you can export those annotations in text format, for example, JSON and XML. So here I need to highlight that, guys, because, and Thomas, you tell me if you guys are doing this, because what I'm seeing, well, what I have seen so far, those annotation efforts like basically get embedded into the model, but you can annotation is data. And I don't think at the beginning of this process we were treating is as data that can be reused, and they would just like go into the proprietary software where the annotations were done, train the model was nice, good, perfect. You change the software, your annotations are gone, you need to start the effort from scratch. So my big ask to everybody who's annotating, if you can keep it as data that's reusable for different platforms, do it, because it's thousands of hours of specialist time, and it's like, I don't know, energy sunk into it, and then it's used once for one model and then it's gone and you have to redo it. And I've been doing that several times, like redoing. We should store them. I don't know, like so now the standardization for slide formats is better than for annotations. But if there's an option to store them and reuse them, let's start doing this, because it's very time consuming and subject to human interpretation, right? So let's treat our annotations as the precious data that it is. And let's talk a little bit about the future emerging paradigms in AI. Obviously, foundation models, and there's gonna be. I can see my heart, right? You can see. We're going to be talking about it. We're just session 3. There is more, but foundation models are emerging technology, multi-model tasks that can handle can involve variety of data types in medicine, and we said that the main categories would be image, text, and then we have genomic data, image, text, tabular data. I think genomic would be in tabular data, right? And combining these all from different disciplines would be. Oh, and we have a lot of questions. I'm going to be addressing them because we're almost done. But what I wanted to emphasize here, and then right, multimodality. I wanna tell you some names. Sometimes people ask me, "Oh, what do you think about histomics?" And I'm like, "What is histomics?" So here it defines that algorithms that merely extract only select features from histopathology slide were called histomics. To those able to analyze hierarchy of novel features in entire whole slide images called pathomics or tissue phenomics. So I think tissue phenomics was invented by the company I was working for, by the Finians. Tissue phenomics. I think we had a symposium, tissue phenomics. But yeah, basically like hierarchy of different features. Next generation histomorphometry, like a lot of terms. But basically what they want to say, different data types, including the image data combinations, right? Another piece of magic, vision transformers. Don't take the piece of magic literally, but these models, these ways of analyzing images, self-attention mechanism, and they can perform both patch level and slide level image classification, segmentation, and object detection. So they still need to divide images into patches, but what they can do after each patch is linearly embedded into a vector, positional information gets added to retain the spatial relationships between patches. I think this is novel. It wasn't the case before. It definitely wasn't the case for multiple instance learning, where you would tile an image into patches and then like let the model predict is it cancer image or not, and it would have to sort, and there can be just one patch that has cancer. So anyway, the transformers do get the patch location information. And the next revolution that I'm seeing happen in consumer AI will be AI orchestration tasks, also in medicine. Um, and oh, you guys are having a cool discussion in the chat. Super cool. Uh, so I'm gonna show it as well. Um, so yeah, AI orchestration combination of text, image, and multi-omics data. And then, in addition, as noted earlier, the classic non-generative foundation models are of great value, and they are of great value in combinations. And what combinations? Like, we will figure out what combinations, what makes sense, where is it, where does it make sense to combine classical with generative, non-generative, with generative, classical with deep learning, and all these things. And the heart wants to show you that ultimately the most likely best solution for a responsible AI approach is one that simplifies the approaches as much as possible, but also may employ a combination of traditional and advanced approaches, with or without generative AI, in addressing the task at hand. And so that's something to pay attention to, especially in marketing messages where they say, like, drop everything else. This is the new thing on the block and just use this. You know what? There is a reason why handymen have a lot of tools in their toolboxes, right? And that counts for AI and for science as well. I recently talked to a group of toxicological pathologists dealing with molecular pathology, and that was one. I was a podcast host for another, for TXP podcast from the Toxicological Pathology Journal, and one of my questions was, "Oh, like, is there the main method?" It was kind of a, like, I knew there's no main method, no solution that solves everything. But I asked them, "Is there like the one thing that people now should be using?" And they say no. They say basically the same. You have your problem and you need to pick the right tool to solve your problem, right? And let me check the chat. Here is what about the representativity when one patient has multiple slides and tumor type and the consequences of the predictions? It should detect multiple tumor types. So depends like how we use. Let me rephrase the question and tell me in the chat if that is what you mean. But basically, when we have the non-generative, non-foundation models, okay, and she's talking about the case with heterogeneous tumors which have multiple divergent differentiation. Do you have experience on that? So I don't have experience, and you guys keep talking in the chat, which is a fantastic discussion. Thank you for this. But I'm gonna present you a concept that could be applied, or like the pattern that I'm seeing. So when those algorithms are being developed, those non-generative AI, non-foundation models, or like non-generative AI foundation models, they have very narrow applications. So it needs to be fit for purpose. And I think we had one publication where there was, they developed an algorithm that will check the data for you and say, oh, is this data good for whatever your algorithm is going to detect? So if we have something that just does, I don't know, I don't want to give a bad example, but like let's do it at a very high level. If there is an algorithm that does breast cancer, and there is a certain types of breast cancer that it was trained on, it's not going to perform on a heterogeneous tumor that has multiple components, right? So the options, there are two options, assuming that option that I just mentioned from the literature is available. You kind of screen the data with whatever method of data data screening you have, um, to check if the tool that you have is going to perform on this data. If it will not perform, don't use the tool. Meaning it either goes back to the pathologist, and Camelia, let me know if this is helpful, or it goes to another algorithm if we have one, right? But that would require upfront knowledge or screening. Okay, do we have the tools that can be used for those images, right? And if we don't, then those images or those cases are set aside as like specialty cases or something that must be reviewed by a pathologist. And that's how I would approach it, because there's no point in using a tool that's not going to be good for the job. Let me check if you have any other questions. And Thomas is saying that he's afraid of pharma R&D. I'm afraid in pharma R&D is quite difficult, weekly or self-supervised learning methods. Yes, I think so too. So I was, of course, and that was in 2019 where I saw the first anomaly detection, and I was like, oh no, that's going to be the next thing. And then it didn't perform, because pharma R&D, because ToxPath is a different, like the different visual presentation of changes. So if it's very obvious, the images. See you at USCAP, Camelia. That's so cool. So if you guys are going to US, how do you pronounce it, by the way? Is it USCAP, ASCAP, or USCAP? I think I'm mispronouncing or mixing the pronunciation constantly. If you can send me in the chat the correct pronunciation of USCAP, then I will use that pronunciation from now on, and I'm going to be at the booth 528. Thank you so much for joining me today, Digital Pathology Trailblazer. And I want to show you something before we go, in case you want to check out and do some shopping, because our store, Digital Pathology store, is live. I didn't want to do that. I wanted to show myself. Here, this QR code, DPP store. You can check it out. So I'm just telling you, it's beta version. It's a work in progress, but I thought if you're interested in checking out the courses, checking out little things like these earrings, you can check out the store. You can also give me feedback on what you would like to see there, what is like totally off, because as I'm saying, this is work in progress, and I would love for you to go there and check it out and let me know what you think. And I talk to you in the next episode.